Hey guys, welcome to DSGN121, Fundamentals of CAD. This is a class that explores the fundamentals and basics of computer-aided design. We do a little bit of dabbling in drafting as well. But for the most part, we'll be focusing on getting you familiar with 3D environment, learning how to use computer-aided design software, CAD software. In this case, this class will be using Fusion 360, and there will be more on that to come. But for this week, we're just going to be focusing on the basics. First thing I'm going to do is actually take a look at the syllabus for this class and just kind of walk through it as I would if we were in person. And don't hesitate to reach out to me if you've got any questions. As you can see, I've got my contact info here at the top. And the way this class is going to work is we are going to be about 90% online, which I know is not the best, but unfortunately it's just kind of the nature of what we have to deal with for the time being. So with that in mind, the 10% that we're not online is what I'm meaning by that is that we're actually going to try to meet once a week. I've put the class time as Wednesday 5 to 6 on Microsoft Teams. And what this is this isn't meaning that we're going to meet for an entire hour every Wednesday. But what it is it's an hour every week. I will probably schedule a Microsoft Teams meeting. And I will likely join the meeting at 5 p.m. on Wednesdays if I am available to. And just check in and see if anybody has any questions about anything particular. Basically, it'll be almost like a lab time for me to help you with anything that we're talking about that week. If for some reason I'm unable to meet, likely due to my day job, I will let you know ahead of time. So just don't expect to meet on those days. But as part of your participation, it would be greatly beneficial for your grade. And for me, to be able to just kind of see where you're at to attend those weekly meetings. So that's happening every week on Wednesday, 5 to 6. Everything else is going to be in this sort of format where I'm going to be uploading a video towards the beginning of the week. I'm going to shoot for Sunday. Sometimes it'll be Monday, depending on how things are going. But most of the time, I will get the content uploaded on Sunday night. Or sometime on Sunday for the upcoming week. And then you'll be able to see your assignments, check in with the video, and kind of watch through it and see what we're going to be going over and examples of me kind of teaching you how to do stuff. It's basically just going to be a tutorial essentially on how to do things, how to use different tools, how to use the program, all that good stuff. So that's what's coming up. Course description, like I said, computer-aided design or CAD, major part of product designer skill set. Study of how to create, edit, analyze, translate curves, surface, and solids. Students will be digitally constructing 2- and 3-dimensional designs for manufacturing, prototyping, material visualization. And upon the course, the completion of this course, you should be able to understand 3-dimensional space, define an object using orthographic views, explode an isometric view into orthographic views, utilize the features of the Fusion 360 user interface. If you're not familiar with Fusion, no worries. If you are, great. We're basically going to be starting from the ground up, so have no fear if you've never used any sort of CAD software. This is the class for you. Basically, all this stuff here is just the basics of what we're going to be going over. The only other thing we're going to be peppering in is some key shot towards the end. And potentially, we'll be looking at a little bit of drafting notation sometime about halfway through. Part of it helps with your midterm, and then part of it is also just good to know. So what we're going to be looking at this week is going to be looking at orthographic projections, which is kind of the bare bones basic intro into how to deconstruct and reconstruct 3D models just from a 2-dimensional perspective. And we will be going over a slideshow a little bit later here where I talk about what that means, give you some examples, and then I will be giving you 2 different assignments. One of them will be to go through the presentation and complete the simple sketches based on those objects. They're very simple. They should be a good introduction into doing it. And then your homework that you'll be doing based on your own will come up in a little bit, and we'll talk about that. But it'll be based on a similar sort of exercise. And those will be both, for this case, I'm wanting you guys just to hand draw them in real life with a pencil and a pen, paper, preferably graph paper. And then just take a photo of it. If you have access to a scanner, great, use that. If you don't, just take a picture of it, clear enough that I can actually see what's on the paper. And you'll be uploading that to the D2L Dropbox. Okay, and further on, I'm not going to explain exactly what every homework is going to be, but just to give you an idea of what's coming up for this week. And looking ahead in terms of topics, we're just going to be basically stair-stepping through Fusion 360 over this whole quarter. And I'd prefer to get right into it as soon as possible, so starting next week, we will be jumping straight into it. I'll be explaining how to download it, how to set up an account, how to join in to the class environment that we'll create, and kind of go over all of the basics of the interface and some of the simple 2D tools. And by 2D tools, I'm mostly referring to sketching. And there will be an exercise for next week as well. Moving forward, we're just going to be moving through different steps, and I'll talk more about these as we get into Fusion because it won't make as much sense until we get there. But basically, you can see here kind of my general layout of how I would like to go through things. Some sections might take longer than expected, so it's all subject to change. But for the most part, we will get you to where you need to be by week 10 for your final project. All right, breakdown of grades. This is weighted, should be weighted correctly, I think. Mostly based on, it's kind of an even distribution of your exams. The couple of projects that you're going to have, those are weighted a little heavier. And then a large part is going to be the exercises that we do every week. And then there is also the 20% that comes down to your attendance and participation. And part of that is going to be not only showing up to the meeting once a week, but I am also going to be posting in the Teams a kind of prompt for you to respond to. So make sure that you are reading these prompts every week and creating a thoughtful, full sentences, at least, several sentences of a response. It doesn't need to be like a huge book reply, but it does need to be something that I can tell that you've actually thought about it. You come up with a response, and in some cases, I'm looking for photos and stuff to be included as well. So, yeah, that's what's going on. All right, grading scale, and then a bunch of stuff that's just normal on syllabuses. So, yeah, that's about all we got going on there. We'll jump back into this presentation here, which is to talk a little bit about the origins of drafting and how we got to where we are. So what you can see here in this photo is what drafting used to be way back in the day. These are drafting tables, and these are draftsmen. And essentially their roles were to take and use tools like these rulers here that you can see, different tools here. They're probably, even some of these guys are using like vellum as like a type of paper to draw on. But their job was to actually hand draft everything. So everything that was ever pretty much constructed. If you look at architecture drawings, you look at electrical schematics, you look at mechanical drawings, all those sorts of things. These guys were actually drafting these by hand, and they were using different tricks and calculations in order to figure all this stuff out. And that was their day in, day out job, was sitting at a desk and drafting. And here's just an old example of something that I found of just kind of like a machine design, mechanical constructions. This definitely is more of a figure. It's not really necessarily going to be used for manufacturing purposes, but you can see here all of the different pen strokes of how this particular piece looks. And you can even see in some cases how they're showing these little dotted lines. Those are indicating that it's a hidden line and that there is something going on that you can't see from the outside. But if it were to be like almost like an X-ray, you could actually see those edges coming through the object. And we'll talk a little bit more about hidden lines and how that kind of plays in a little bit. So then we're going to skip forward to just talking about the invention of the computer. So again, CAD is computer-aided design. Before computer-aided design was computer-aided drafting. So again, same thing here. You can see here he's got a drawing here that was probably hand-drawn by somebody. And then he is now using this nifty interface here to create a digital version of this drawing. And so he is using this, and he's using a computer-aided drafting software in order to take the real drawing and turn it into a digital drawing. And these kind of things over here are pretty interesting. When you look at toolbars in a lot of programs today, this is kind of what was the grandfather to toolbars, was that you actually had this stylus and all of these different things here are commands or tools, and he would just touch them with the pen there and it would communicate back to the software what command that it was trying to run. So this is like way before we even had interfaces or mouse to work with, but this actually was using that sort of iconography, I think it is called. Yeah, anyways, and then he's got some sort of other scanner, printer, something or other. I'm not entirely sure what this is. Probably wouldn't be a scanner. And here's another couple examples, whether these likely predated the previous photo, but again, you can see here that they're using pens and they're actually interfacing with the computer. And you can see here that there's all these different inputs for different options. And you can see here the object in front of him is kind of what he looks to be drafting there. And so yeah, this is kind of like the stair-stepping of how that works. Here is a little bit more modern. This is obviously sometime, I want to say 80s would be my guess, 80s or 90s. Probably not quite 90s based on this interface. But this is where Autocad became a thing. And Autocad, you may have heard of it, you may not have. Autocad is the OG, still used heavily to this day, CAD software. And AutoCAD is purely two-dimensional. So all of this stuff here you're going to be creating in AutoCAD is all going to be two-dimensional drawings. And again, everything that they're creating is a drawing so far. We haven't even gotten to the part yet about design, because that was kind of the way it worked, was that you would actually design things by hand and then draft them up in the computer. And then around the time, obviously, of some of the computer invention stuff, they started doing design stuff more in computers, but it almost always was in the context of a drawing. Very rarely were you just creating an object for an object's sake. It was like you were creating a drawing and a design at the same time. And again, you can see over here the same kind of interface toolbar sort of thing that I was talking about. This is a very similar approach, but obviously at this point, they seem to have keyboard and mice. So the usage of this is kind of in tandem with that. And here's a picture of somebody in the modern age using a modern modeler that looks like Inventor, maybe? Autodesk Inventor. And this is where you see now kind of what is now considered the norm, which is that we actually design things with computer-aided software, and then we use those designs to create drawings based on those designs. And that's kind of, I want to say, a somewhat new thing, in that we're actually able to create three-dimensional models that can then be converted into two-dimensional drawings. And the reason we do two-dimensional drawings is because the way that manufacturing processes exist, and especially existed for a long time, was you only had the ability to work in 3 dimensions, X, Y, and Z. And so there was no point in having a 3D model because you could only ever actually work in the 3 different dimensions. And then throughout time, you start getting the advancement of machines, where you start getting a 4th axis, a 5th axis, a 6th axis. And all of these different machines are now able to create fully 3-dimensional geometry with a single machine, which is incredible. It's awesome. 3D printers are another example, right? You take a 3D object in the computer, you just hit the print button, and you're able to print that entire 3D object all at once. That kind of stuff did not exist for a long time. And so again, what we are looking at is I'm kind of going to teach you the basics first, looking back at how we first learned how to do computer-aided drafting, where we're going to be looking at 2-dimensional drawings, and we're going to be learning how to construct and deconstruct 3D models into 2-dimensional drawings. And so that'll be kind of what we're looking at. So here's a more modern example of a drawing. And this thing here is a centrifugal fan type. And what we see here is very classic sort of things that you will find on a drawing. First of all, you've got your border here with its indicator for grid. And you've got your information down here in the bottom right corner, talking about who like the customer is, or who the person is that's manufacturing it, the name of the drawing. This sort of thing here refers to, this is like a drafting standard symbol that refers to how to read this, the scale of the drawing. So this is 1/28 the size that it would actually be, which means if you were to measure this with a ruler, this dimension is 5,610 millimeters. But if you were to measure this with a ruler in real life on a piece of paper that this is printed out, that would be exactly 1/28 the size of the full size. And what we see here is the isometric view is what this is referred to as. And something to say about isometric is that the way that you view things as a human is with 2 eyes. And there's this thing called depth that plays into that. So because you have 2 eyes, anytime you're looking at any objects, you have a perceived idea of depth. If you were to close one of your eyes, or you were to use something like a camera, or a camera, I suppose, isn't always true, but closing one eye, you can remove the depth aspect and have something that you see straight lines, if that makes sense. So what I mean by that is that if I were viewing this with 2 eyes, I would actually see the kind of cascading of these legs downwards, inwards likely, because my eye is perceiving the legs coming from the different directions because I can see it in 2 different points, and this whole thing would be looking like it's coming out of the page. It gives it that perspective look. So we usually refer to that as perspective, and what we refer to as everything that we do in CAD is usually referred to just as orthogonal. And what orthogonal is it means that we're imagining that I'm closing one eye and I'm looking at this object so that every line, if there's something directly behind this that's the same size as this, they look exactly the same and they line up exactly. I hope that doesn't confuse you. Please let me know if any of this doesn't make sense. But basically what I'm trying to say is that we get a very clean view of what we're looking at when we imagine that we're looking at it orthogonally. If we were to draw it with perspective, it would look quote unquote more realistic, more artistic, more like it's jumping off the page. But that's not helpful when we're trying to do things like grab dimensions and look to see how big something is, and basically any sort of drawing stuff. So what you will find is almost everything in a drawing is orthogonal. And isometric is essentially what it looks like when you look at something from an angle that is orthogonal. So what this means is that this object is not in perspective. So that means if I were to draw a vanishing point on either side and draw my lines, these lines are not going to vanishing points. They are on a grid. It is very structured. This square here is exactly the same size as this square here, so on and so forth. Like, it's exactly correct. And that's isometric is essentially just the three-dimensional, the version of an orthographic view that is showing the 3 dimensions in one view. Here is a more simplified version. Probably should have led with this one, but alas, here we are. Isometric view. So you can see here again, if I were to draw, this would be a perfect cube. That's an isometric cube. And then we have our left side view, our front view, and our top view, which is often referred to as a plan view, because if you imagine a building and you were to look at a building from the top, you would have the floor plan. So that's kind of where that name comes from, is because it gives you the overall plan of what it is that you're looking at. So isometric, showing the three-dimensional, you see that it's got 1, 2, 3 holes. It's got this kind of L shape on top, L shape on the front, L shape on the side. And then what happens with this is this gets broken into 3 different views. And essentially what this is it's imagining we're looking at it from straight down, straight from the left, and straight from the front. Okay? And that's what we see here. So here, this corner is this corner. This chamfer is that chamfer. And we're looking straight down at it. We see some dotted lines here. This implies that there are edges there. Every single line that is represented on here is representative of an edge. So here you can see the circle there. That's representative of the edge of this circle. Same thing over here. Edge, edge. The dotted lines just mean that we can't see those edges. And so what it is it's a representation to show that from looking down at the top, we are confirming that there are in fact hole cutouts, and that is what they would look like from the top. And then we look at the front, there are hole cutouts. That's what this one would look like from the front. And then from the left, we can see that there's one here, and then there's also a cutout here on the left. So 3 different views. If you were to put all of these together, you get a idea and a full picture of what the isometric view would look like. Okay. There are some more specific things to talk about in regards to terminology, and I should probably talk about that in this image. So a couple things. The flat areas are usually referred to as surfaces and or planes in some cases. And what it is it's just a planar face. and that's usually just a surface. And the edge is where two surfaces meet. So where this surface meets this surface, that creates an edge. And then where an edge and an edge meet, that is usually referred to as a vertex. So you have your surfaces, your edges, and your vertices. So that's just kind of an understanding of where these come from. So in this case, when we look at it from the top view, we can see all of the edges that are visible. And that's about it. Even though that these are curved, these are different surfaces here, it doesn't matter, because what matters is the straight, hard edges of where the surfaces are meeting. Anytime you have the geometry that kind of flows from one to the other, where it's kind of this smooth transition, and there's not actually a hard point, that's a continuation of the surface. So this would all be considered the same relative surface. Some softwares will cut it up different ways, and again, we'll kind of talk more about that later. Here is a floor plan. Another example of using drafting and using 3D design to create these sort of floor plans. So CAD is used not only for mechanical parts, but it's also used for things like architecture and creating things like floor plans. Here is a example here of a part that was created in a 3D CAD software. And we can see here that it's displaying here what all of the dimensions are, because the main purpose of CAD, and as drafting has always been, but in this case it's just in a computer, is to fully define an object within a 3D space. So previously, way back at the beginning when we were drawing on tables, those guys' job was to fully define an object in a 3D space on paper. And they had to make sure that they had all of the dimensions, so that if I gave you that stack of papers and it gave you access to a machine shop, you could make exactly what's on those drawings. So in this case, that's exactly what's going on here. We have this object here, and every aspect of this object has been defined here. So we know exactly how wide it is, and we know how wide it is because we can see that from the edge of this to the center of this hole is 21, center to center is 50, and guess what? Same thing on this side, 21 from here to here. So that makes 41, and then 41 plus 50 is 91. So therefore, we would know that the width of this plate is 91. The length of it is 142. Hole distance there. And then again, you can see that they only say the 21 once, because we don't need to say it multiple times. And that's kind of something that will come with time. I don't expect you to be able to fully understand fully defined and underdefined objects, but we will get there. And the main thing to understand is that you usually don't have to put a dimension twice unless there's you want to make sure that it is correct. Otherwise, it's just implied that it's the same. So anyways, that's what you see what's going on here. And then in the CAD space, all we're doing is just defining that object through a series of features. And ultimately, then you can create a drawing based on that design. So here's an example of something in Fusion 360, which is what we will be using. And again, I'm not going to talk about everything that's going on here, but just to give you an idea, this over here on the left is kind of what makes up this object. It's a series of sketches, and these are all two-dimensional sketches. And using these sketches in a combination with features, which you can see down here, this is kind of the timeline of things as they're happening. And with the combination of the sketches and features, they're able to create a three-dimensional object that has been defined within its respective three-dimensional space here. And here's an example of SolidWorks. That was a simple object. And eventually, as you go up in complexity, you get to the point where you're creating assemblies, which are essentially a collection of multiple objects. So each of these objects has been defined within a coordinate system. And then each of those objects needs to be defined within the coordinate system of the entire assembly so that you can assemble all of the different parts together. So that's kind of just to give you an idea of where this is going. Is we're kind of starting at the base, very bare bones, which is how do we define a simple orthographic shape. And then by the end of this quarter, we will be to the point where you will understand how to create an assembly and how to assemble a bunch of defined objects within an assembly. So to start with the basics, we're going to be looking at orthographic projections. And I briefly talked about it just a little bit ago and showed a bunch of different examples of orthographic projections. But just to make sure that everyone understands, we're going to start with very basic and kind of step up in complexity. I will show you me drawing an example, and then we'll kind of end on that note. So for starters, again, looking at this simple Tetris L shape, this is the classic example. And what we see here is a side view, a front view, and a top view. And an important note that I didn't really mention before has to do with the orientation of where these drawings are and how they correlate with one another. So the orthographic, as I've already mentioned, refers to kind of the nature of the view and how we're looking at it as if we're closing one eye and there's no depth of field, there's no vanishing points. It's straight on, simple geometry. The projection part I did not talk about, and what that refers to is how you can project the image from one view to another. And that is represented here with these blue lines that you can see. So we'll start here with the front view, which is going to be from this green arrow looking at it from this side. If I wanted to draw the side view, I'm going to imagine that I'm taking this object right here and I'm rotating it 90 degrees relative to where I'm looking at, and then I'm going to be drawing that view. So I take this, I rotate it 90 degrees, so this vertice right here is going to become this vertice right here. So this one moves over to here. And this whole thing is rotating 90 degrees as if it's coming out of the page at me. These blue lines are representing the fact that you can use the information from the first view to create your second drawing, which is that this edge is going to be shown right here. The top edge is going to be shown right there, and the bottom edge is going to be shown right here. So anytime that there's an edge, we need to illustrate it. If it is visible to your eye, it is going to be a hard, solid line. If it is something behind what it is that you can see, it needs to be dotted lines. Again, with the top view, we're going to take this and imagine that we're rotating it 90 degrees this way. So this point will then become this point over here. So again, starting with this point, rotating it up, and it becomes this point. Again, we're just inferring from our front view to create our top view. So it projects from this view down to this view. And we get this edge here, this edge here, and this edge here. Okay, here's a slightly more complicated one here. So we've got this C shape with a hollow cut out through it and a hole cut out through it. So we'll start with the top view, and we can see that it's a square shape here. These cut out here, there and there, are illustrated with these dotted lines here. And that shows that if I were to look at it straight down with my X-ray vision, I would see dotted lines where those edges are. circle, it appears as a hard solid line because I can see that hole cut out right there from the top. We then take this, we rotate it 90 degrees. In this case, this edge becomes this one. This one kind of rotates back almost, and it moves down here. We can see now that these edges become hard edges because we can see that with our eye, but we can't see the hole cut out anymore, so that needs to be dotted lines. And you can see here these little dotted lines that are showing here. You don't need to show these on your work. However, that is why I recommend using graph paper, because if you draw things on a grid, you can use those grid lines to project from one view to the other, and it'll make your work much quicker. So then we take this and we rotate it 90 degrees again, rotating it so we're looking at it from this side as if we're looking at it from over here. And you can see here the hole cutout is the same. And this edge here, which is that inside edge, becomes visible right here. And so we make sure that it's a dashed line because we can't actually see it, but we do know that it exists, and so we need to include it in there. Okay. And one more example here, simple example to look at, is this sort of same kind of C-ish shape, rounds off, has a what appears to be round piece out the back, and a hole cut through those two things there. Looks like some sort of link. Isometric view, looking at it from the angle. Then we got the top view, and this one's also showing dimensions. If for whatever reason you were trying to recreate this, or in this case, because this is almost a drawing. And again, the reason I know that this piece here is round is because of the third view. If you haven't noticed already, anytime something is cylindrical, it does appear as a square until you look at it straight on, and then it's round. And then that is how you can determine whether or not something is round. So, like I've been saying, the whole point of these drawings is to convey all of the information that you need to be able to 3D construct an object. So it gives us all the information that we need in this view to know how far apart this part is, how big the channel here in the middle is, how thick these pieces are here. This view tells us how big that circle is, the cutout for the circle. This tells us the length of that part there. This tells us the diameter of that round part in the back. And then all of these dotted lines are confirming that we're looking at the same object, and these are also confirming the geometry that we believe to know is true. So for example, these cutouts go all the way through, and we know that because we can see that there's a cutout here, and when we look in this view, we can see that those dotted lines are going all the way through in this view and in this view. And this section here that's cut out, there's no hidden shelf down here. And we know that because we can see the dotted lines showing that that whole thing is cut out. Okay. Hopefully that made some sense. Again, feel free to reach out to me if you do have questions. And when we meet on Wednesday, definitely be sure to ask me if we have questions. All right, moving on to the example portion. So I will be using Illustrator. It just is a good, nice tool to help illustrate what I'm trying to do. And this presentation here will be uploaded for you to use on your first exercise, and your homework will also be uploaded as a separate PDF. So we're going to be using this as my example that I'm going to be drawing. And this is the case of what all of these will be. So you can see here, they're all different examples. I will be drawing the first one here, and then all of the rest of these will be on you to complete on your own. And they kind of step up in difficulty as they go down. So first one, pretty basic. These are pretty basic, and then it moves up. This gets a little bit more challenging, a little bit more challenging. So do your best, and if you're able to make some progress on it before Wednesday, great, and then we can discuss it if you have any questions. So for this example here, my preferred kind of layout is usually something like top, front, right. This doesn't particularly matter. What does matter though is that if I were looking at one view, each view should be the correlating projection. So for example, if I have a rectangle here, looks like I need to make it show up like a stroke. If I have a rectangle here and I wanted to look at it from the front, my front view should not look like this. And then my right view looks like this. That would be incorrect because this is not a projection down here. However, if I were to swap these like so, this would then be correct, because I wonder if I have to have like a nice big arrow. Maybe not. Basically, this is projecting down into this, so we're looking at this edge here is going to become this edge. This face becomes this face, and then this face becomes this face right here. And it's projecting from top to front and then from front to right. So you can't just skip from top to right. You could if this was over here. And again, this is where I'm saying that like the order doesn't matter, but how you orient it does. And again, this would be still incorrect if I did it like this. However, if I were to rotate it 90 degrees, this would then be correct, right? Top, right, front. So hopefully that little illustration makes sense of what I'm meaning about your order of how you lay it out. So I'll go ahead and draw this one here. And nice thing about Illustrator is it does have a lot of these inferring guides, which will kind of help me to illustrate what the projection aspect is going to be for you guys. So first of all, we'll start with the top. So it is going to be a rectangle of sorts. And then up here, I've got what looks to be square. And so my little pink line that comes from corner to corner implies that it's square. I'll even go ahead and place that in the center. And then relative to that, I'm going to draw another one that's the same width, that's maybe a little bit shorter, like that. And this is going to be my round cylinder here. Because remember, again, round cylinders show up as squares unless you're looking at them straight on. So that would be my first view. Looking straight down at the top here. And if I really wanted to, I could go in and I could label this and say, this is B, this one's going to be F, this one's going to be A. But here you can see these are where my projection lines are going to come in. So from the front, I can infer that this is going to be square. And you can see that it lines up with where my lines are for the top view there. And then I can draw my top piece here. Again, I'm making it a square. And then my front piece here, obviously I don't have an indicator of how far it's placed on this, because that is why we have multiple views, is because you can't convey that information in the top view. So I'll go ahead and make it, I know that it's supposed to be that far out, and it's supposed to be approximately something like that. If I really wanted to, I could even take this piece, copy and paste it just to make sure I get the right height. And I will make sure that the center of this is lined up with the center of that. Perfect. And then for my front or my right view here, I'm going to, again, do the rectangle portion. And again, this distance should correlate to be the same as this distance here. So in this case, I will actually just use the same one just to make sure that it's exactly correct. In your case, using graph paper, I expect you'll be able to count how many squares you drew and then do the correlating amount of squares over here. It's important that your drawings are to scale relative to themselves. And what I'm meaning by to scale is that, for example, you see how big this is compared to this. They're at two different scales. But my drawing here is correct to the scale of itself. So I'll go ahead and do my rectangle, make sure that it's the same height, make sure that it's right in the center, and I will go ahead and do this guy. Yep, that looks all good there. And again, this one actually needs to be a circle. I drew the square there as a reference to make sure I know how big it needs to be. And let's see if I can draw my ellipse. Is it gonna let me? Guess not. We'll see. Place that in there. There we go. So there I know that it's touching all those edges. And then I've got my right view there. Okay, so it's basically just working its way around, starting with the top, inferring information on the front, using the front to infer information on the right, and all of this together equals up my 3D image here of this isometric view. Okay, so what I'm expecting for this exercise is for you to create the top, front, right for every one of these objects. So in total, you should have 1, 2, 3. Those are two different objects. 1, 2, 3, 4, 5, 6, 7 different sets of three drawings. So each one of these should have a top, a front, and a right. Okay, so that's orthographic projections. Again, if you have questions on those, let me know. Hopefully that was understandable, and as you work through these exercises, hopefully it should make more sense, and then that way by the time you get to your homework assignment, you will be good to go. Let me know if you have any questions, and yeah, thanks for watching.